Hello everyone. Let's try the paper 2, variant 2-1 of the CIE AS A Levels 9702 code and year October November 2023. All right, the first question. Compare scalars and vector quantities. So whenever we are asked to compare two quantities, they're not just asking about the differences, they're asking about the similarities also. So when we talk about the similarities, or just similarity, basically, both require numerical magnitude. But the difference is that vectors require directional or direction, whereas scalars do not. Scalar quantities do not. Okay. The radius of a small sphere is determined from a measurement of the volume of the sphere. The sphere is submerged in water, displacing some of the water into a measuring cylinder as shown. Measuring cylinder, displaced water. So basically this is one of the applications of Archimedes principle, where the object displaces the volume by the same amount as the volume of the object itself. So the measured volume of the displaced water is 28 plus minus 0.5 centimeter cube. Calculate the radius in centimeter of the sphere. So volume of the sphere, we have done this in maths also in secondary classes. So that's 4 over 3 pi r cubed. So radius would be written as 3v over 4 pi cube root. So we have cube root of 3 times by 28 divided by 4 pi. So we get 1.88 since we're given the volume in two significant figures. So let's just use two significant figures over here, 1.9 over here. 1.90. Okay. The percentage uncertainty in the radius of the sphere. Okay, so the percentage uncertainty. So the radius, as we can see, is coming due to the cube root of 3 over 4 pi. This is a constant, so there is no uncertainty in this. But it's also coming with the cube root of the volume. So this is the one, this is what's contributing to the uncertainty in the radius. So to get the radius, fractional uncertainty in the radius times by 100%, we need to do the 1/3 because this is the power. 1/3 of the fractional uncertainty or the percentage uncertainty in volume. So this is 1/3 of what the volume was, 0.5 over 28 times by 100%. So we get 0.5 times by 100 is 50 divided by 3 times by 28. This is 0.595. So we're just going to use one significant figure is enough, 0.6%. Okay, all right, moving on. A hot air balloon floats just above the ground. The balloon is stationary and is held in place by a vertical rope. The balloon has weight W of 3.39, 10 raised to power 4 newtons. The tension T in the rope is 4, 10 raised to power 2 newtons. That means 400. Upthrust U acts on the balloon. The density of the surrounding air is 1.23 kilograms per meter cube. Okay. On figure 2.1, draw labeled arrows to show the directions of the three forces acting on the balloon. Okay, so we know that uh, upthrust will be causing the balloon to go upwards. Weight is bringing it downwards. And we have, oh sorry, what was the third one? The tension. Now the tension is goes always, it always goes away from the object, so this is going to be downwards for, oh sorry, let's make that again. This is T. Okay, all right. Calculate the volume to three significant figures of the balloon. Now for the volume, what we can do is we can use upthrust is equal to rho GV, where this rho is the density of the medium, and this is upthrust, and this is the volume of the object. But over here, we don't know what the upthrust is. So if we look at our forces, we know that the upthrust is going upwards, and weight and tension are going downwards. And since the system is in equilibrium, we know that this means that upthrust is equal to weight plus tension. So this means that this system is equal to the weight plus the tension. So the volume will just simply be equal to weight plus tension divided by rho g. So weight is 3.39 times by 10 raised to power 4 plus tension is 400 divided by rho, which is 1.23 times by 9.81. So 3.39, 10 raised to power 4, I'm sorry, plus 400 divided by 1.23 times by 9.81. This is 2,842. So we have the data in three significant figures. So let's keep it to three significant figures. So 2842.6. So the final volume that we'll actually write is 284 T meter cube. Okay. The balloon is released from the rope. Calculate the initial acceleration of the balloon. So when it is released from the rope, so that means there's just upthrust and the weight now. So the resultant force is just coming from the upthrust minus the weight, and that will be equal to the MA. So where M is going to come from the weight over G, and upthrust we calculated right over here. So upthrust minus, since upthrust before was just equal to weight plus T, so when we do upthrust minus W, that will be just equal to, the magnitude wise, it will be just equal to tension. So if we just use the same 400 equals to the weight that was 3.39, 10 raised to power 4 divided by 9.81 times by A. So A would be cross multiplied Oh, sorry, 400 times by 9.81, sorry, 9.81, 3.39, 10 raised to power 4. We get A as 0.1157. Again, just three significant figures, or yeah, so that will be just 0.1. I think two decimal places are also fine. 1, 2, we can say. Meter per second. All right. Okay, so the balloon is stationary at a height of 500 meters above the ground. A tennis ball is released from the rest and falls vertically from the balloon. A passenger in the balloon uses the equation v squared is equal to u squared plus 2as to calculate that the ball will be traveling at, at a speed of approximately 100 meters per second when it hits the ground. Explain why the actual speed of the ball will be much lower than 100 meters per second when it hits the ground. So this is due to the air resistance. So as when it falls initially, it will have the acceleration of 9.81, and as it carries on, the air resistance increases. So the air resistance increases with speed. So there will come a point when air resistance becomes equal to the weight, and that is the point when it just travels with a constant speed, no acceleration. So we don't know if that's the case happening over here or not. Well, all we know is that acceleration is less. This is just due to the air resistance increasing. So as the ball falls, as the ball falls, initially its acceleration is equal to acceleration due to gravity, but as the speed increases, the air resistance increases as well, which reduces the acceleration of the body of the ball, thus reducing final velocity. Okay. Before the balloon is released, the rope holding the balloon has a strain of 2.410 raised to the minus 5. Okay. The rope has an unstretched length of 2.5. The rope obeys Hooke's law. Show that the extension, so strain is equal to x over L. So we need to find the x, strain times by L. So strain is 2.410 raised to power minus 5, and the unstretched length is 2.5. So 2.4 times by 10 raised to power minus 5 times by 2.5. 6, 10 raised to power minus 5 meters. Okay, so calculate the elastic potential energy EP of the rope. So EP is equal to half f of x, fx. We know that before the rope was released, it had the tension of 400 newtons, in the rope, and that is the force that's causing the extension. So that will be half times by 400 times by the extension 6 10 raised to power minus 5. So half times by 400 is 200 times by 6 times raised to power minus 5. So that is 0.012 joules. Okay, all right. The rope holding the balloon is replaced with a new one of the same original length and cross-sectional area. The tension is unchanged and the new rope also obeys the Hooke's law. The new rope is made from a material of a lower Young's modulus. Okay. State and explain the effect of the lower Young's modulus on the elastic potential energy of the rope. So if we look at the formula, that is the stress over strain, which is the F over A over X over L, which simplifies to FL over AX E. So a lower Young's modulus, so if we just compare between the old FLAX and the new FLAX, the force is the same, the tension is the same. So if you want to take a ratio basically, so the tension is the same, this means this cancels out. Same original length cancels out. The cross-sectional area is the same. So the only difference is coming in the extensions. So this is the case and the second case. So now the only effect, so since this E1 was greater than E2, and this all just boils down to 1 over x1 greater than 1 over x2, so when we take the reciprocal it will be the opposite. So x1 would be less than x2. So the extension in the first case is lower than the extension in the second case. So, so what we'll do over here, or what we'll write over here, due to a lower Young's modulus, the extension in the new rope will be higher. And how does the extension help us? The extension is the half Fx. It affects the elastic potential energy that way, which will increase elastic potential energy because they are proportional to each other. That's it. Okay. A trolley A moves along the horizontal surface at a constant velocity from towards another trolley B, which is moving at a lower constant speed. in the same direction. Okay. Table 3.1 shows the data for the trolleys. Trolley A, mass 0.25, initial speed. Okay. The two trolleys collide elastically and then separate. So elastically means that the kinetic energy is also conserved and the momentum is also conserved. Resistive forces are negligible. Shows the variation with time t of the velocity v for the trolley B. Okay. Okay. State what is represented by the area under the velocity time graph, that is the displacement. Actually, it's the net displacement, but displacement is also correct. Use table 3.1 and figure 3.2 to determine the acceleration of the trolley B during the collision. Okay, so the change in velocity over change in time. So acceleration is the change in velocity over change in time. So actually we should write this over here. Change in velocity over change in time. So let's see what are the 2 points over here. So we have 0.15, 0.12, and the next point is 0.35, and that is 0.3. Right, okay. So we're going to copy them right over here. Oh, sorry. Right, okay. So the change in velocity will be found from these two. So 0.3 minus 0.12 divided by 0.35 minus 0.15. So the acceleration is 0.3 minus 0.12 divided by 0.35 minus 0.15. So 0.9. The magnitude and direction of the final velocity of A. So this is velocity, not the speed. So velocity is just rising. This means that not only it's in the same direction, but the change in momentum is also upwards. So magnitude and direction of the final velocity of A. Okay, so we need to find the A. Okay, all right. So since the collision happened, and the change in velocity was positive for the trolley B, and so will be the m times by v, the change in momentum for the object B, for the trolley B. That will be opposite for the trolley A because momentum is conserved. It will be opposite for that. So the change in momentum that trolley B faces, it will be equal in magnitude, but in opposite direction to that one. So if we find out the change in momentum for this one, the change in momentum is just for trolley B, that is the mass 0.75 times by 0.3 minus 0.12. So 0.75 times by 0.3 minus 0.12, that is 0.135 kgs meters per second. Now the trolley A will face the same, will undergo the same change in momentum but in the opposite direction. So minus 0.135 mass of A, V minus U. So that is going to be we will just solve this out. 135 mass of A was 0.25. Final velocity is missing. The initial velocity, that was 0.48. So by solving this, we get minus 0.135 plus 0.25 times by 0.48 divided by 0.25. Minus 0.135 plus 0.25, oh sorry, times by 0.48 divided by 0.25. So this is 0.06 minus 0.06, which means that minus 2 indicates in the opposite direction. So magnitude is 0.06 and the direction is opposite to the initial direction. Opposite to the initial direction. Opposite to initial direction. On figure 3.2, sketch the variation of the velocity of trolley A with time t from time 0 to 0.5. Okay. So, right. Okay. All right. So, the the collision will happen in the same time frame. So, let's draw two lines over here. And right over here, oh sorry, no, let's draw that again. Right, okay, so almost on the line, this and this also, if we, okay, all right. Now since the collision is happening in between these two, it will be the same for the time A. For the time A, it was moving at initial velocity 0.48. Now 48 is somewhere over here, so let's use 48. Let's use a different color. So 0.48. Okay, and then it changes to 0.06. 0.06 would be somewhere over here, 0.0246 over here. So right over here. So now the change in velocity from this point to this point. That's it. That's our graph. Sorry, it's taking a little bit time because, I don't know what the problem with OneNote is. But otherwise, this is how it's going to go. See, from 0.48 to 0.0 minus 0.06. Okay, all right. All right. So state the principle of superposition. So this is easy. When two or more waves meet at a point, the resultant displacement is the sum of individual is the sum of displacements of individual waves. Okay, so coherent light. So the coherent light is incident normally on two identical slits, X and Y. The diffracted light emerging from the slit superposes to produce an interference pattern on a screen positioned at a distance of 1.9 meters from the slits. Figure 4.1 shows the arrangement and central part of the interference pattern of bright and dark fringes on the screen. Okay, so the separation of the slits is 0.65. The distance between, so this is our A, the distance between the centers of the adjacent bright fringes is 1.7 millimeters, so this is our X. Calculate the wavelength lambda of the light. So we know the formula. Lambda is equal to AX over D. So A is, so we have to convert them into meters. Yes, meters. So 0.65, 10 raised to power minus 3. X is 1.7, 10 raised to power minus 3, divided by 1.9. Yes, okay. So we have 0.65 times by 1.7 times by 10 raised to power minus 6, minus 3, and then divided by 1.9. So 5.82, 10 raised to power minus 7. So yes, two significant figures. So just 5.8, 10 raised to power minus 7 meters. So the light waves from the slits X and Y in B arrive at a point between adjacent bright fringes on the screen. Figure 4.2 shows the variation of the displacement with time t for the waves arriving at the point they meet. A student makes two statements about the waves at this point. Phase difference between the waves is 90 degrees. The amplitude of the resultant wave is 0. Okay, so since they were talking about the point between adjacent bright fringes, so they are talking about the dark fringe. And for the dark fringe, we know that the path difference is the calculated as odd multiples of half wavelengths, where n is 1, 2, 3, and so on. And when this is converted into the phase differences, this is converted into the odd multiples of 180 degrees. Oh, sorry, odd multiples of half 360 degrees. However, let's look at the diagram over here. So at this point, at time is equal to 0, one of the waves, which is the wave from the x, is at 0, and the wave from y is at the maximum point. So yes, if we look at the sinusoidal waveforms, one is starting from 0, the other is starting from the maximum point. So this means that they're out of phase by 90 degrees, or a quarter of the cycle. So yes, okay, so let's write this. So waves x and y are out of phase by 90 degrees, or quarter cycle, as because at time t is equal to 0, because at t equal to 0, x is at 0 displacement, 0 displacement, whereas y is at maximum displacement. Okay, state and explain whether statement 2 is correct. The amplitude of the resultant wave is 0. So the amplitude of the resultant wave will only be 0 if the waves are out of phase by 180 degrees. Okay, so that's the condition, that's when they destroy each other. That's the definition for the destructive interference. However, since the phase difference between them is 90 degrees, so that's not going to be the case, as you can already see that 0 and, let's say for example, whatever this maximum displacement is, the resultant displacement will be right over here. And at this point over here, it will be right over here. So somewhat going like this. So, and again, they have something over here, so maybe somewhere over here again. Somewhat like this. This is a very crude diagram, but now we know. So incorrect, as the waves are not 180 degrees out of phase. The waves, the resultant displacement will be non-zero. Okay. Okay. The width of each slit in B is decreased by the same amount. Okay, all right. There is no change to the separation of the slits. Describe and explain the effect, if any, of this change on the appearance of the interference pattern. So basically what they're doing is they're reducing the aperture size. So when we reduce the aperture size, the brightness uh, of the fringes gets lowered, or the what we just call as intensity, basically. So reducing the width, reducing slit width reduces intensity of light, incoming light, which further reduces the intensity of bright fringes without any change to fringe spacing. So basically, the contrast will be lowered a little bit. Okay. Okay. So a train travels at a constant high speed along a straight horizontal track towards an observer standing adjacent to the track. The train sounds its horn continuously as it approaches the observer from time t is equal to 0 until it is well past the observer at time t is equal to 2. The train passes the observer at time t1. The horn emits a sound wave of constant frequency fs. Okay, all right. On figure 5.2, sketch the variation of the frequency of sound heard by the observer with time t. Right. So we have the observed frequency when the source is approaching. That is V divided by V plus V minus Vs, Fs. And for the receding, we have V plus Vs, Fs. So this is for approaching, and this is for receding. So they're roughly constant. So uh, when the train is approaching, this will be roughly higher, slightly higher than the source frequency. And after it recedes, while it is receding, it will be roughly horizontal. So somewhat like this. Okay, at a particular time, the sound waves at the observer have an intensity of 4.7 10 raised to the power minus 3 watts per meter square. The waves at the observer are incident at right angles on a circular detector of radius 2.8 centimeter. Calculate the power of the waves incident on the detector. So intensity is just power over perpendicular area. So if we just want to find the power, we need to multiply the intensity with the cross-sectional area. Since it's a circular detector, so it will have a circular cross-sectional area. So intensity is 4.7 10 raised to the power minus 3, and that is pi. Radius is 2.8 10 raised to the power minus 2 whole squared. So 4.7 times by 10 raised to the power minus 3 times by pi multiplied by 2.8 10 raised to power minus 2 whole squared. So we get 1.15, sorry, 1.16 10 raised to power minus 5 watts. So just to make sure that we did the calculation correct, intensity 10 raised to the power minus 3 pi r squared, the radius was converted into the meters whole square. Right. Okay, so we get, right, okay, so we can convert this into two significant figures, so 1.2 10 raised to power minus 5 watts. Okay, a battery is connected in a circuit with a light-dependent resistor LDR, two fixed resistors, and a voltmeter as shown in the figure 6.1. This is the LDR, this is the constant resistor, voltmeter, and the EMF source. Okay. So the battery has an electromotive force of 25 volts, negligible internal resistance. Resistors have a resistances of 320, 240. Voltmeter displays a reading of 16 volts. Show that the current in the battery is 0.05 amperes. Okay, so we can find the current flowing through the battery by just finding the current passing through this resistor. So how we can do that, we know the potential difference across this. So V is equal to IR. So I is equal to V over R. So potential difference across the 320. One is 16, resistance is 320. So 16 divided by 320 is 0.05 amperes, does show. Calculate the resistance of the LDR. Okay, since this is the EMF is 25 volts, the potential difference across the parallel branch, the potential difference across LDR, is equal to 25 minus 16. That is going to be 9 volts. And we also know that the current will be branching with due to the Kirchhoff's laws over here, Kirchhoff's current law, the current will be branching. So if we can find the current, we need the resistance, right? So we can actually find this using potential divider formula also, but let's keep things simple. So if we find the current to the 240 ohms resistor, we can find the current to the LDR. We already know the potential difference, so we can find the resistance. So the current through 240 ohm resistor is equal to IV over R, 9 divided by 240, which is equal to 9 divided by 240, that is equal to 0.0375 amps. So current through LDR is equal to 0.05 minus 0.0375. So that is 0.05 minus answer, that is 0.0125. So what we can do now is resistance of LDR is equal to V over I, that is 9 over 0.0125. So 9 divided by answer, which is 720. So pretty straightforward. Determine the ratio power dissipated in the LDR, power dissipated in the 240 ohm resistor. So power dissipated in the LDR is I square R L L, and the I square R R square I squared R. So the current passing through the LDR was 0.0125 whole square times by 720 divided by 0, 0.0375 times by 240. So we have 0.0125 whole squared times by 720. Then we have 0.0375 whole squared times by 240. So we have 1 over 3. So 1:3. So the intensity of the light incident on the LDR increases. State and explain what happens to the voltmeter reading. So the first thing that will happen is that the resistance on the LDR will decrease. So as light intensity decreases, the resistance on this LDR decreases. What this will do is this will further decrease the combined resistance of this branch, because the REFF depends on the R of the LDR plus the 1 over 240 basically. So if this is also decreasing, if the LDR's resistance is also decreasing, it will further decrease the resistance of this combined branch. So when the combined branch resistance when the parallel branch combined resistance decreases, the voltmeter reading will rise because the potential difference across the 320 ohm will increase as compared to that. So let's write this as light intensity increases, the LDR's resistance decreases. This reduces the combined resistance of parallel branch, which would lower which will lower the potential difference across LDR and increasing potential difference and voltmeter reading across what was that name, 320 ohm resistor. Right, okay, moving on. The results of the alpha particle scattering experiment led to the development of nuclear model for the atom. State the results that suggested that most of the mass of the atom is concentrated in a very small region and most of the atom is empty space. So observation number one was most of the alpha particles passed through with deviations of angles less than 10 degrees. The second observation is that a small proportion of alpha particles were deflected back with angles greater than 90 degrees. State the composition of gamma radiation. So this is just electromagnetic radiation. Electromagnetic radiation or wave, or we can also say gamma photons. Okay. Table 7.1 lists the name of three particles and possible classifications for them. Neutrinos. So neutrinos are leptons. They are neither baryons or hadrons because they are not composed of quarks. Neutrons are hadrons and baryons because they have three quarks, no antiquarks. Positron similarly is just a lepton. Okay, all right. The discovery of a particle with unusual charge was an important step in the development of theory of quarks. The particle is a hadron with a mass of 2.19 to 10 raised to the minus 27 kgs and a charge of plus 2e, where e is the elementary charge. Calculate the mass in atomic mass unit of the particle. So we know that 1u is this is given in the data sheet in the start of the paper. So this means that just to find that, so we just need to divide 10 raised to the power minus 27 with 1.66, 10 raised to the power minus 27. So just 2.19 divided by 1.66, that is 1.319, so that is just 1.32 U, atomic mass unit. Determine a possible quark composition of a hadron with a charge of plus 2e. Explain your reasoning. So we know that a proton has u, d, up, down. So that it leads to the charge of plus 1e. So if you want a plus 2e, we could try u, where the charge would be plus 2 over 3e plus 2 over 3e plus 2 over 3e combines to get 6 over 3e, which is just 2e. Oh, sorry, 2e. Plus 2e, sorry. Let's use plus 2e. Since we just need the plus 2 over 3, plus 2 over 3, plus 2 over 3, we have more possible combinations also. Since we know that up, charm, and top have 2 over 3 plus 2 over 3e, and down, strange, bottom have minus 1 over 3e. So any combination of up, charm, top would give us this plus 2e. So we could use the up, we could use charm, 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 top, 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 up, charm, top, anything Any combination of up, charm, top would give us the plus 2e total charge. Okay, so this is the end. See you in the next paper. Bye-bye.